Week 12, Part 1, Refraction of Light. So when we did Maxwell's equations, we came up with traveling waves. And if I want to draw those, we can imagine the electric field is oscillating up and down along a direction that it's traveling like this. So it's propagating in that direction. And you have to really imagine that the electric field is not just pointing in that direction right there, but it's pointing in that direction all along a plane here. These are sort of wave fronts or wave crests, they're sometimes called. It's like a surface of like a plane, that everywhere on that plane the electric field would be pointing that way. And if you moved it back here, now the electric field would be pointing that way. Everywhere on this plane, that's what is propagating. These things are propagating along like that. And we're not going to be using this sinusoidal description of it very much at all anymore. In general, we're going to be more concerned with the direction of propagation. And so we'll draw rays like this that show the direction that it's propagating. And sometimes we'll also show these wave fronts going across the rays like so. So that's our picture of light propagating. Now, what happens when light encounters a different material? What happens if we come to a boundary or an interface, and now behind this is maybe glass or water or some other transparent material? What would that look like? So out here, imagine that this is either air or it's vacuum, which behave essentially the same for our purposes. And that's where we solved Maxwell's equations in the vacuum and found how it propagated. What happens when we come to some kind of transparent material, like glass? What then? Well, if you recall, we did Maxwell's equations in the vacuum. So here's Maxwell's result. And what we found was that the speed of light, and we gave it the letter c as the new name for that. We don't call it the velocity anymore. It's just c, is 1 over mu naught epsilon naught, if you remember. But that's in the vacuum. That was true in the vacuum. In a material, it turns out that the velocity of these waves, the wave velocity, it's a very similar formula, but it's 1 over mu and epsilon without the naught. It turns out that if you're in a material, these two parameters, mu and epsilon, have different values. And the result of that is that in a material, the speed of light, the wave speed, is slower. It slows down. And what we do then is define something that sort of characterizes that material, puts it all together, rather than having to keep track of what's mu and what's epsilon in these materials. All we really want to know is what is the speed of light in them. And so an index is defined, and it's defined kind of upside down. At least it seems like it, at least at this point, the way we define things. N is the index that characterizes this material and tells us something about how the speed varies in that material compared to the vacuum. And N is defined as the speed in vacuum divided by the speed in the particular material that you're talking about. Now that seems backwards. Normally you put the particular divided by the reference, and here it's the other way around. You have the reference value on top and the particular value in the denominator, with the result that even though the speed is slower in the material, n will be larger. And so just for some examples, glass has a value of the index n It's about 1.5 for many glasses. It can range up commonly to 1.6 or even all the way up to 1.8 for some very special types of glass. But most commonly it's about 1.5. It can be just a little bit smaller. Different types of glass have different values. Water is another thing that we'll commonly work with, and the index of refraction for water is 1.333. And so you should realize this means that in glass, the light is traveling slower than it is in water. Water is closer to the vacuum value. On the other hand, to go the other direction, we can talk about diamond. Diamond has an index of refraction of 2.4. So the speed of light in diamond is much, much slower. It's almost 2.5 times slower than it is in vacuum. And one more thing I'll mention is air. The speed of light in air isn't quite the same as it is in a vacuum. It's ever so slightly slower, and the index has 3 zeros and then a 3, or you can put other digits in there. That just gives you an idea of how very near it is to being the same as vacuum. Now, what this does is this causes an interesting thing. The picture I've drawn up here is where a wave would be encountering a surface perpendicular. And in that case, the wave just slows down, carries on in the same direction, but it slows down. What's interesting is when you have a wave of light encountering a boundary, but at an angle of some kind, not perpendicular. And then it causes bending, or we call that refraction. And you can understand this in a very crude way by just imagining that if this is a slower speed material here, and you're trying to get from one place to another, let me draw this over again down here. So here's a region that's slower, and out here is fast. So slow speed and fast speed. And you can think of this in a couple of different ways. One is just say this is a swimming pool, and you're trying to get from here to here. This is land, and you want to get from here to here as fast as possible. Most of us, in fact, all of us, swim much slower than we can run. And so you would presumably run somewhere like this and swim like that, take a much shorter path. And so there'd be a bending like that. Your path would not be straight, and light does something of the same thing. It chooses, it turns out, what amounts to the quickest path between 2 points. So when it encounters a material in which the speed of light is slower and it's coming at an angle, then it turns, and so it ends up picking what amounts to the quickest path between 2 points. That's one way to think about it. There are others. You can imagine the ranks of a marching band with everybody marching along side by side. Here are the marchers walking side by side, taking even steps, all the same. And when they encounter this part of the field, it's muddy or something like that, I don't know, then just imagine that they now shorten their steps. They still march in time, but take shorter steps. What will happen is that the entire band will turn and will start moving off at an angle. And that is the same thing that goes on with light again. Let me just be a little bit more explicit about how that works and show you with some nice diagrams. This whole idea comes from Huygens. Christopher Huygens was an English scientist, And his way of understanding wave propagation was that if you have the crest of the wave here at some moment, then you imagine each point on that crest is itself producing a new wave that spreads out from there. And so that's what these circles are. These are imagined to be the wave that spreads out from that point, and here's the wave that spreads out from that point. And as those each generate sort of the successive wave and spread out, do you see how they all come together and form a new line? And so that's how the wave kind of progresses in that fashion. But you can use this construction to figure out what goes on in a couple of situations. Here's one. This is what happens when a wave encounters a mirror. So here's our wave front. These are the points. And those produce this little wavelet, if you like, this little ripple that spreads out. And then we construct the succeeding wave by just connecting them together with this dotted line. And then you do it all again. So you draw the new wavefront and so on like that. And you get the wave coming like this. Now imagine that this is coming up to a mirror, but that we don't yet know how mirrors behave. We only know that they don't allow the light to progress on into the mirror. They somehow scatter it back in the reverse direction. We'd like to work out what angles the scattering happens at. Well, let this propagate forward a little bit. And then what you do is you take this point, and now it can't scatter in the forward direction. So we let it scatter in the backward direction. And then this one is just starting to scatter. Wait a little while later, and these two are scattering there. And this one's spreading out like that. And this one is just beginning. And you see, we recreate these lines, but now they're going back up the other direction. And the important thing to note is that the angles are the same. So the wave as it came in was the wave fronts, or the wave crests along here, were at an angle we'll call θ1 with respect to the mirror surface. Another way of expressing that, and the way we'll more commonly use it, is to look at a ray telling you the direction that this wave is moving, and measure the angle between that ray and the normal to the surface. If you remember in lab, I talked about this. We always measure the angle with respect to the normal. So again, that's the same angle. These two are the same angle, theta. You can prove that if you want. The important point of this whole derivation is to say that when a ray comes in at an angle θ1, it reflects back at exactly the same angle, just on the other side of the normal. So it came in on this side of the normal, and it goes out on that side of the normal. So you get equal angles of reflection. That's sort of how Huygens proves that. It's something you kind of already knew. It seems sort of obvious, but here is one that's not so obvious, where Huygens becomes a little bit more useful. So start with the same idea, but this time it's a glass surface that isn't a mirror. And so we're going to allow the wave to propagate into the glass. But as with the marching band example, as we proceed, you can imagine that we're drawing these dotted lines for a wavelength. Each one of them represents exactly one wavelength. So we've gone one cycle to the next wavefront. And we strike the glass here, and it propagates on in, but the important point is, in one cycle, in one period of this wave, these little ripples will not travel as far inside the glass as they were traveling outside the glass. And so this distance in here now is a shorter distance. It's still a wavelength, but the wavelength has changed. The frequency has not changed, but the wavelength has changed. The wave has slowed down. So at the same frequency, the wavelength is now shorter. So because this is slowed down, you see that the dotted line has to slant a little bit. And even after two of these, then you get a line connecting all of these along here. And it has changed angle a little bit. And here, without all of the extra labels and such, you can see how it changes a little bit further. And eventually, the wave is progressing down inside the material. But do you see how it has a different wavelength than it did up here? And it's moving at a different angle. And so it started out at theta 1 up here, and down here it's theta 2. Or we could have drawn it, and probably should have drawn it, where here's the normal, and this would be theta 1. And down here, I don't have as good a place to put that, but maybe I'll do it like this. And keep this one going here, and this would be theta 2. And so you notice that it has bent, and if you think of it in terms of the normal, it has bent toward the normal. Theta 2 is a smaller angle than theta 1. Now let's see if we can be a little more specific about this and derive the actual mathematical relations involved here. And what we're going to be doing is looking at this figure right here. If you just look at this kind of weird quadrilateral, I guess it is here, with a line through the middle, we can work everything out just from that. So here is kind of the same picture. And I have just picked out that one same figure right there. And then I'm going to go even a little bit further and look at all of the angles in here. Now, for whatever reason, I've changed from theta to phi. Some books use phi, some books use theta. And I did it both ways here. I'm sorry about that. But anyhow, once again, here is phi 1, or what we called theta 1 over here, the angle. It's the same thing as the incidence angle. Again, I could have defined it over here. I just didn't. And here is the angle inside the material, phi 2. And what we'd like to do is see if we can figure out a relation between those two that involves the speed of the material, of light in the two materials, in the two mediums. This is done actually in a totally general case where medium 1 has some speed and medium 2 has some speed. Neither one of them has to be air or vacuum. We'll get a totally general relation this way. So looking at these triangles again, if you think about it, well, here's a right angle in both of these. So they share a hypotenuse. I've labeled that as H. And out here is the wavelength out in material 1, and here is the wavelength in material 2. That's one wavelength worth. So looking at these two triangles, you can write these relations down here, that the sine of phi 1 equals lambda 1 over h. Sine of phi 2 is lambda 2 over h. Solving for h and equating them, that's what this is down here. That you get lambda 1 over sine phi 1 equals lambda 2 over sine phi 2. Now, remembering once again that when the medium changes, when the light enters a new medium, the velocity changes, the wavelength changes, but the frequency is still the same. So velocity being frequency times wavelength, that's a basic relationship. We can solve this and say that wavelength is velocity divided by frequency. And so the wavelength in medium 1 would be the velocity in medium 1 divided by the frequency. The frequency is the same. I don't need an index there. They have the same frequency. And similarly, lambda 2 is V2 over F. And then what I'll do is substitute these expressions for lambda 1 and lambda 2 into this equation up here. And what we get down here is V1 is f over sine phi 1. V2 is f over sine phi 2. And now the f's are the same, so we can cancel them out. And then I would like to just flip this whole thing over. So if you want, you can do a whole bunch of cross-multiplying, rearranging, but it amounts to the same thing if you just say, we're just going to flip these, both sides of the equation. And so then we'd have sine phi over v, and then I also multiplied by c for reasons that you'll see in just a moment. Multiplied by c. So this is the expression we get. C times sine of phi 1 over v1 is c times sine of phi 2 over v2. And now if you just remember our definition for the index, it was the speed of light in vacuum. That's what we call c, divided by the speed of light in the medium, which I'm calling v, v1 or v2. So then you could use n1 to talk about the index of material 1 and n2 material 2. And each one is c over the v in that material. So this n is the same thing as c over v1 here. This n is c over v2. And so you have this expression down here. And this is known as Snell's law. So if you know the indices of refraction, and you know one of these angles, you can get the other angle. In other words, if we have light impinging on if light is directed toward a surface, and we know the incidence angle, say phi 1, and say it's coming from air, and so we know the index of refraction for air is essentially 1, and we know what kind of glass we have, then we know everything in here except phi 2, and we can solve and find the angle of the wave as it now propagates inside the glass. That is Snell's law. It's very useful for calculating the refraction of light when it encounters a surface.